Over to question 2, a question about a motorcycle. Mr. Watling must be having a gay old time doing this one. A motorcyclist riding on a level track is told to stop via a radio microphone in his helmet. The distance d travelled from this instant. Okay, from this instant told. So this is making me think of, if I was to put velocity, time, I suppose this is almost high school. You're travelling at your maximum speed, you get some sort of stimulus to make you apply the brakes in an emergency situation, but you have a certain time delay for that to happen, and then you start stopping. So this area of this section is going to be the thinking distance, and the area of this section is going to be the braking distance. Let's read on. From this instant and the initial speed v are measured from a video recording, right? Bloody blah. A student is investigating how the stopping distance, so stopping distance equals thinking distance plus braking distance. That's going to be the total area of these two sections. The stopping distance of a motorcycle with high performance brakes varies with initial speed. Explain why the student predicts that v and d are related by the equation. Okay, well, I'm seeing that will be the triangular section, that will be the rectangular section. Here's the rectangular section, triangular section. So let's see if we can get the same equation just by looking at this graph. Let's add a few extra details though, because down here it says where A is the deceleration of the motorcycle, so that's going to be the gradient of that line there, I suppose. And T is the thinking time of the rider. So that means I need to label this part of the graph is small t for thinking distance. But I think for the purposes of working out the area of this section, I'm going to need to use a different letter to represent this time, and I'll just use capital T there. The total distance travelled is going to be the total area underneath this section, which is going to be the area of that rectangle, which is going to be velocity times small t, the thinking distance. The length of that side times the length of that side will give me that area there. Plus, this is a triangle, so I need a half base times height deal. The base can be capital T that time, and the height is going to be v as well. So this is my beginning equation. Acceleration is the rate of change of velocity, so that's going to be dv by dt. In this particular case, that's going to be from maximum velocity all the way down to 0, so v minus 0 is just v, and the time for that to happen is going to be capital T. So I can rearrange this to make t the subject, and I've got v over a. I can then substitute that in to this equation, and I end up with d equals vt plus, and now I've got a half, and instead of t I'm going to do v over a times v, which is v squared, and I've got something that's beginning to, well, looks exactly like the equation at the top there, so I suppose just rearrange it now to make it look exactly the same. V squared over 2a, just doing that bit first, plus vt. So this is the area of the triangular section of this curve, of this graph, and this is the area of the rectangular section. Stopping distance is, in this case, braking distance plus thinking distance. Part B, the student decides to plot a graph of d over v on the y-axis against v on the x-axis. Best way to do this is to draw it to start with. They're suggesting d over v on the y-axis, v on the x-axis. Let's take our equation, d equals v squared over 2a plus vt. Let's rearrange it to make d over v the subject, so we can see what sort of y equals mx plus c type deal will spill out for us. So d over v equals, so v squared divided by v is just v over 2a plus the v would disappear plus t. And we've got v on the x-axis, so finally I'll write this in this style. D over v equals, and then I'll put 1 over 2a, close brackets, open brackets, v plus t. This way I've got y equals mx plus c. I think this is possibly a sensible choice, because if you read the blurb, I suppose these are going to be your variables. These are the things that are going to change, and everything that's part of the intercept must be a constant. I presume that the deceleration is going to be a constant. I presume that the rider's thinking reaction time is going to be a constant as well. So translating that over to our graph, we're expecting a straight line graph with a positive gradient and a y-intercept. The gradient would be equal to 1 over 2a, and the y-intercept would be equal to the thinking reaction time of the rider there. So quite what they want for 2 marks, not really sure, but explain why this is a sensible decision. This will produce a straight line graph with 1 over 2a as the gradient and t as the y-intercept. Now this will only occur if both a and t will need to be kept constant. If they are to function in that y equals mx plus c, will need to be kept constant during the experiment. There you go, I feel better with that as an answer now.